Coming up on Dr. Kiki Science Hour, we're talking about thorium reactors with Kirk Sorensen. That's up next on Dr. Kiki Science Hour.
Netcasts you love.
From people you trust. This is Twit.
Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki Science Hour with Dr. Kiki, episode number 84, recorded on Thursday, February 17th, 2011. The Nuclear Alternative. Welcome, everybody, to Dr. Kiki's Science Hour. I am Dr. Kiki Sanford, and yes, today, it's another day, it's another episode, it's more time for more science. I know you're excited. I always am before the show gets started, and it's always a good conversation. Today, 1 hour, one topic, one expert. You ready to dig in? Because we're about to dig into the topic of liquid thorium nuclear reactor technology. Is that a mouthful? Have you heard these words before? Well, today we're going to learn a lot about what this technology is. It's possibly a cleaner, greener alternative to the current uranium nuclear technology that we use. With us to talk about this liquid thorium reactor today is Kirk Sorensen. Kirk, from his Twitter profile, is a nuclear technologist, aerospace and nuclear engineer, and a thorium enthusiast. He runs the Energy from Thorium blog and has been interviewed by the likes of Wired magazine and invited to speak at Google. He's been championing thorium reactors for years. And why has he been doing that? And is he finally starting to be heard? Hopefully today we'll get some inkling of answering these questions. Kirk, thank you so much for joining me today.
Thank you very much, Kiki. I'm glad to be here.
It's great to have you on the show. This is a topic that I think is really interesting. From my own perspective, looking at nuclear technology, looking at issues of energy, alternatives to coal, oil, what energy we have available to us. We look at, sometimes, a lot of people are looking at nuclear technology as an alternative. And we look at it with the commonly used, since about the 60s, the uranium based nuclear reactors. But what you're talking about is using thorium instead of uranium, and instead of being a solid core nuclear reactor, such as are used with the uranium reactors, would be a molten core reactor. Why the differences and how? I know this is a big question, but how is thorium potentially better?
Okay, let me talk about the fluid-fueled reactor initially and why that is a very interesting and compelling concept for a nuclear reactor. It seems different than what we've seen before or heard about before as far as using solid nuclear fuel to produce energy. But the story behind the fluid-fueled reactor dates back to some of the early pioneers in nuclear energy, particularly one named Eugene Wigner, who was a Nobel Prize-winning physicist. And he looked at a nuclear reactor as a chemical reactor. His training was chemical engineering. And so he thought, here's a machine that takes one kind of material, uranium or thorium, and turns it into a different kind of material. And so it was important that he figure it out from a chemical perspective, how to add new fuel as the reactor was operating, how to remove the byproducts of the reaction, and how to keep things going. And he naturally thought about his background in chemical engineering using fluid and gaseous streams, and so he conceived the idea of using a fluid-fueled reactor. And it seemed very logical to him, and he had a young protege named Alvin Weinberg, and Weinberg kind of caught the bug from Wigner, the idea of a fluid-fueled reactor, and began to pursue the technology at Oak Ridge National Labs in the 1950s. Another thing Wigner was interested in was the use of thorium. He knew that thorium was more common than uranium, and it had some advantages in nuclear reactors. It could be completely consumed in what's called a thermal reactor, unlike uranium, which has to be consumed in a fast reactor to be fully consumed. And so Wigner married these two ideas, the fluid-fueled reactor and thorium, together, and he and Weinberg came up with a very compelling concept.
Now, the concept, it's been around since the 1950s, you said, 1950s, 1960s, and then it stopped. What happened to completely arrest the development, the research going into the liquid fuel reactor back in those days, and that continued, that allowed the solid fuel to move forward?
That's a very good question. The solid-fueled reactors got a very early start in the Navy program under Admiral Rickover. They were developed to the point where they were powering submarines, and then they were the technology that was the most developed when it came time to move reactors onto the land in 1957. We began building power reactors. There was also a situation where when you use uranium in a reactor, you make plutonium. And the technology to separate plutonium and uranium from one another was being developed under the weapons program. So that was something that the nuclear industry, by and large, felt comfortable with. They thought there would be advances in uranium and plutonium, and everybody was behind the solid-fueled reactor. Wigner and Weinberg were out on kind of the fringe by advocating liquid-fueled reactors and thorium, and they had some good physics behind them, but when the project was killed in 1970, and it was killed when Weinberg was fired from the leadership of Oak Ridge National Labs, he later on wrote in his memoirs in the 90s that he felt like the knowledge of the technology was too geographically concentrated, that basically only people in Tennessee knew about liquid-fueled reactors, and it wasn't widely known, and so there wasn't a lot of support for it. We didn't have an internet back, well, I guess we did have an internet, but not a lot of people used it back then. And so I think what we have now is we have an opportunity to disseminate these advantages worldwide through the use of the internet, things like this show, and have a discussion about maybe we took the wrong turn. Maybe thorium was the right way to go, and the liquid-fueled reactor was the right technology. And I believe it is. I think it solves the basic problems that people have against current nuclear technology.
And so let's talk a little bit about that. The main problems that people have with current nuclear technology are, number one, safety. Is it going to melt down? Are we going to have an accident where there's radiation release into the local environment? Secondarily, what about waste? What are we going to do with the materials that are left over that are going to be, we're going to have to put them in some kind of a containment for how many thousands to millions of years? I think those are the main, and then additionally, nuclear security. A lot of the byproducts can be used for weapons. So how does the thorium technology compare to that uranium technology that we're currently using?
Well, I'll start with safety, and the safety record of today's nuclear industry is absolutely unparalleled. We've been running reactors in the Western world for 50 years without any deaths caused by nuclear power, and you'd be hard-pressed to find any other energy generation technology, including wind, solar, hydro, whatever, that even comes anywhere close to that safety record. So I think the safety record of our nuclear technology today is outstanding. As an engineer, I know that safety record is purchased at a price, that we have a lot of backup systems and backups to backups and so forth, what's called engineered safety systems in today's reactors that make that safety possible. The compelling possibility that you can have with a liquid-fueled thorium reactor is what we call inherent safety, and that's where you only have one safety system that will work 100% of the time because it's based on passive processes like gravity. And even today's nuclear industry is working to getting closer to this, but the liquid-fueled reactor has an amazing safety feature. If it begins to overheat, there's a little plug of frozen salt at the bottom of the reactor vessel that will melt, and then the salt will drain into what's called a drain tank where it's passively cooled. And this is a system that doesn't require any computers or human intervention or anything. In fact, we actively have to keep it from happening. So if you turned off all the power to the plant it would safe itself automatically. Even in cases of severe damage or accident, it will safe itself automatically. And today's reactors will also safe themselves automatically, but they have computers and pumps and pressure systems that do this. So this is a possibility of achieving an even higher level of safety than what we have today. And I really can't say enough good things about the way our nuclear reactors have operated from a safety perspective. I mean, it's really outstanding.
Yeah, I'll agree with you. I'll agree with you there. I mean, there's no question that the safety issues have been addressed over and over and over again. But there is the question of, as we move forward, are there even safer ways to do it? And so it sounds like the liquid thorium reactors, they do add to that safety standard.
Yes, they do. They do. We can achieve what I would call it is we can achieve safety for less cost because we're moving to passive safety rather than engineered safety. And we see this trend with reactors, say like AP1000, but the lifter can take it to a much higher level.
So let's talk about waste products for a second. What happened? What kind of waste products does a thorium reactor have?
Okay, that's a great question. I'm glad you brought that up. One of the things that bothered early nuclear pioneers was how poorly you could do on fuel efficiency with uranium in what's called a thermal reactor, which is a normal kind of reactor. You could only burn up a little bit of the energy in uranium. Normal, natural uranium contains less than 1% of the isotope uranium that will fission, uranium-235. And our reactors can't burn up even to that level. And so we end up producing a lot more waste than we would like. And really, most of that waste is unburned fuel. And there are ways to reprocess it and burn more of it, but it's quite expensive and it's not economically advantageous in today's reactor. So that's why we're not recycling to a great degree. On the other hand, the breakthrough in going to fluid fuels means that you don't have to reprocess or recycle. You leave the nuclear fuel in the reactor until it's burned up, and you add fuel as you need it, and you remove the fission products as they're generated. And so you can approach nearly 100% burnup in the fuel, and that's just incredible. That's outstanding. And that's what can reduce the waste stream from the lifter by about a factor of 300 over what we have in uranium today. On top of that, the thorium itself is very common. It's 4 times more common than uranium. So it's just it's a huge improvement in the waste profile when it comes to using liquid fueled thorium reactors rather than solid fueled uranium reactors.
So thorium is more naturally abundant, and when it comes down to it, it burns up more completely, and we have less of the waste. I read somewhere that the waste that is produced is actually valuable waste that can be resold for other processes. Is that correct?
Well, that's actually common to both uranium and thorium-fueled reactors. Both produce fission products from fission. It's just that the quantity of material you're dealing with is literally like a factor of 300 to 1.
Okay. In terms of the materials that are produced, with uranium, we're processing. You have plutonium as a byproduct. You have other uranium. What is it? Uranium-233. There are other isotopes of uranium that are left over. What is left over from the thorium reaction?
That's a very good question. I think what you're referring to is the transuranic isotopes. Basically, everything heavier than uranium on the periodic table: neptunium, plutonium, americium, curium. Our current uranium reactors produce this stuff, and it is the material that kind of gives people who are thinking about like a Yucca Mountain type repository the headaches, because it has long half-lives, tens of thousands of years, and we worry about how to contain it. Now, the advantage of using thorium is you're starting about 6 atomic mass units lower on the scale when you begin to burn thorium, and so you can burn it up far more completely, and you can generate about 1% of the transuranic material that you would do in a uranium reactor. Now, what's interesting is that 1% you would generate could also be extremely valuable. I gave a talk at Google about this last month on how we could use lifters to produce plutonium-238. Now, plutonium-238 is a specialized plutonium. It has no use in weapons. It's used to power space probes that explore Jupiter, Saturn, the outer solar system. And NASA is in desperate need of this material in order to continue space exploration. We're not able to produce it in our existing reactors, but with LIFTR we could. And so even that 1% we produce from LIFTR would be tremendously valuable.
Yeah, it sounds like it would be. I mean, being able to maintain a process in which you have products that come out of it that can continue to be used for valuable work, that, you know, it seems beneficial on all fronts. I noticed there's something on your website about uranium on your website, your energy from thorium, about uranium-233 and the I guess there are some plans for within the government to take current uranium-233 storage that we have and to downgrade it, to get rid of it. And you're arguing that we should, to save money for the deficit, not do that.
Yeah, there's a lot of good reasons not to destroy the uranium-233, and saving money is just one of them. This uranium-233 is very special. We don't have very much. We only have about 1,400 kilograms, and it's all formed from thorium. Uranium-233 is the fissile material into which thorium is transmuted when you put it in a reactor. So all the uranium-233 in the world comes from thorium, not from natural uranium. It sounds a little confusing, but they really are very different. This material can be used to jumpstart a lifter. This is what we can turn these machines on with. And if we are able to start it with U-233, we can minimize the production of the types of transuranic isotopes like plutonium, americium, curium we don't want, and we can maximize the production of plutonium-238. When I say maximize, I mean we're talking probably 10, 15 kilograms a year of this material, but that's the amount NASA needs to explore space. There's another incredible feature of uranium-233 that I only recently became aware of, and it's so exciting to me that I almost lay in bed at night thinking about it. There is a special product that comes from the decay of uranium-233 called Bismuth-213 that can be used to fight very difficult to reach cancers. What they do is they take this bismuth and they attach it to an antibody, and it goes into your body and it finds the cancer cell. It locks on, and then the bismuth decays and destroys the cancer cell. And I thought, wow, this is incredible. It turns out it's a very unique material. If we destroy this uranium-233, we have no other way to produce this special bismuth-213 that can be used to fight cancer. And that's why scientists, doctors, even the Inspector General of the Department of Energy have begged Congress and the Department of Energy not to destroy this material. It can save tens of thousands of lives, and it can fight some of the hardest and most difficult cancers out there. I just think the lives that we could be saving with this material, it's so exciting.
Yeah, so in a number of different ways, saving the U-233, we've got space exploration, we've got saving lives from cancer, there are a number of applications, things down the road that could come from it, that if we didn't destroy it. Why are they planning to destroy it? Just because there's no other way to get rid of it? Is it just hanging around and they don't know what else to do with it?
My understanding of why this decision was made is not fully complete. I've been trying to piece together the story, but from what I understand, it's stored in a building at Oak Ridge, and about 15 years ago, the people who had it asked around and said, you know, does anybody in the government want this? We can't just give it to anybody, but does anybody want it? And basically nobody said we wanted it. So they wanted to decommission this building at Oak Ridge where the material was stored, and in order to throw the uranium-233 away, they had to go and downblend it first before a waste site would take it. And so once this downblending is mixing uranium-233 with uranium-238. Once we do that, we destroy its value in LIFTR. It will never be good again as a nuclear fuel for us. We dilute it so much that it's no good for the NASA mission or the medical isotopes mission. And so I really want to find somebody in the federal government, you know, maybe it's the Department of Defense, maybe it's NASA, someone who will stand up and say, we need this material. Please stop the plans to destroy it and save it for future generations that are going to make electricity from it and other products.
Just to clarify, somebody in the chat room was asking for a clarification on LIFTR, and that's the abbreviation of liquid fluoride thorium reactor. correct?
That's right.
Okay, so anytime you mention lifter, for anyone in the chat room, anyone who's listening to this conversation, it has to do with the liquid thorium reactor that we're talking about. So I'm thinking about where this technology is going, how we can get it applied. It sounds like, on many fronts, it would be superior, or at least on par with what we're currently using for our nuclear technology. Where is it in terms of development? You mentioned before that in the 50s and 60s, not that many people knew about it. So people really weren't working on it. It wasn't being discussed widely in nuclear engineering and technology circles. Where is it now? How many people are talking about it? Here in the United States, we still don't have any plans in the works to develop it further, really, but other countries are talking about it.
Absolutely. And right now we know that there is an active program in China to develop lifter.
Yeah.
I wish I could tell you right now that we have an active program in the United States. I'm working to try to start one. We have a community of online enthusiasts, some of whom are nuclear engineers, some of whom are other scientists and engineers, some of whom are good at getting the word out to the public. And so I think things will proceed differently this time than they did back in the 50s and 60s. Back in the 50s and 60s, you had government appropriations to national labs, which led to development of this technology. I don't think that's how it's going to happen this time. I think it's going to be a fusion of the enthusiasts and private industry that is making this happen, with government essentially overseeing and regulating the activity rather than being the leader on this. Because enough people now, thanks to the internet, are learning about the potential of lifter and thorium, and they're asking hard questions to their leaders like, okay, why aren't we doing this? And they're finding there's no real good answer. And then the next part's even more fun, where they go, well, I'm going to help. I'm going to get involved. And that's why we started the Energy from Thorium Forum. It's why we have the blog and the Twitter feed and the Facebook page. And all of that, I think, is just the beginning to what I believe in the next few years is going to become a true, honest-to-goodness development effort instigated by individuals in the United States to make this happen.
What do you think it's going to take? I mean, we're looking at right now, I know there are a number of traditional nuclear plants that are in the planning stage or in the regulatory paperwork approval stage, just getting them approved. We're not in a state of building nuclear plants here in the United States right now as it is. Things are really not getting built. There was a website. I found a website that it was mentioned that as of like 2007, that lifter was potentially the most easily scalable, low-cost technology available for rapid replacement of fossil fuel-generated energy. Mass production of lifters in factories is possible, and that enough lifters could be built by 2050 to supply a greatly expanded world energy demand. Do you think that's true? Do you think regulation is going to get in the way?
Well, let me take the first part of your question and then feed into the second part, because I think they connect. Yeah. We have a limited amount of nuclear construction going on right now. At Watts Bar 2 in Tennessee, they're finishing the Watts Bar 2 reactor. There are 2 new reactors under construction in Vogel in Georgia. Now, this construction is exciting, and I applaud it, and I hope it goes forward. But right now, we're just holding the line against the retirement of the other 104 nuclear power plants in the country. And even if we have significant builds of reactors, we will just be maintaining the amount of nuclear power we generate in the country, not expanding. If we want to reduce our carbon generation and replace coal, we need to envision a future where we're producing much, much more nuclear reactors than we are now. And that's where I think Lifter has a incredible story to tell, due to the fact it runs at atmospheric pressure, due to the fact it can be built in very compact units in factories on an assembly line. We need to be producing these reactors like the way Boeing produces 737s. We need to be producing these like one a week, instead of the way we build light water reactors today, where we go to a site and spend 5 years pouring concrete and building buildings and so forth to get the reactor online. We need to be able to mass produce reactors if we are going to turn the tide against fossil fuels. Because I think while what we're doing now in the nuclear industry is exciting It's just holding the line. If we're going to expand clean energy in the form of nuclear energy, we have to look at a nuclear technology like LIFTR that is much more amenable to mass construction than the light water reactors we have now.
Yeah, the light water reactors, on average, it takes about 15 to 20 years from conception to actually getting them built. And that kind of a length of time is it's too much. We're not going to.
It is. And we're hoping to do this faster. In China, they're building light water reactors in about 4 years, which is a lot better. But we haven't proven yet that we can build a light water reactor that fast in this new generation of build. And like Vogtle 3 and 4 will be a real trailblazer for the industry. How fast can they bring those two reactors online? If they do a good job, there will probably be a bunch more orders for light water reactors, a bunch being 5 or 10. That's great, but that still just holds the line against the retirement of other nuclear power plants rather than actually expanding our nuclear generation capability.
Yeah. Where is the technology currently? I mean, are we at a point where within the next 10 years or so, could we see these, I guess, conveyor belt lines of LIFTR parts getting put together? How long do you think it's going to take?
At the rate we're going now in the United States, it'll never happen, but that's going to change. Yeah. So we're going to start. We're going to change things. We're going to make it happen. I think in 10 years we will be building lifters in factory assembly lines. In fact, I'm betting my future on that very vision, and I'm convinced that if we don't do it, it will still be happening. It will just be happening in a place like China rather than the United States. But we will be seeing lifters built in the future, make no mistake. Our only question is, will the Western world assume a leadership position in this, or will we sit back and be purchasing this like so many other things from China?
Yeah, and China recently said that they are going to be pursuing LIFTR technology, and if they put their mind to it, their workforce to it, the way that they've put it to other technologies, they're probably going to move ahead very quickly. Do you think that the United States is going to be taking that, as a threat and seriously?
Well, I welcome what the Chinese are doing with LIFTR. I think it's a great thing for them. Obviously, they have a huge population. They have a huge need for energy. I think they're making the right choice by investigating thorium and LIFTR technology, and I think it will. I have a high confidence that they will succeed. But I want us to succeed too, and I want us to be able to bring these systems online for our own benefit and for the economic benefits that our nation can reap by being a leader in this technology. And I hope that doesn't sound selfish at all, because I really do wish the Chinese the best of success, but I want to see us be leaders in this technology. This was the place where it was invented. This was where all of the fluoride reactors that have been demonstrated were done, and I think it is the appropriate place for us to go forward in the future.
How big would the average thorium reactor or thorium power plant be? What would it be, on par with what we're looking at for current nuclear facilities?
A LIFTR that was capable of generating about 1,000 megawatts of power, and that's a pretty standard size in the industry, excluding the heat rejection system, would probably comfortably fit on a football field. And that's a pretty significant reduction in size. When you compare that with other technologies that are generating the same kind of power, it's really going to be a small footprint. It's one of the things I love about this technology is the amount of land that we need to devote to doing this is tiny. I used to be very interested in solar and wind, and one of the things I didn't like about them was how much land you had to devote to those things. And usually it was land that was far away from where people live, so you had to figure out how to do transmission from where the power is generated to where it's going to be used.
Yeah,
we can build these reactors on very small pieces of land and, rather close to demand centers. And so it excites me that we can meet our energy needs for a whole lot less land area than other technologies.
And do you have any estimates on what the cost would be compared to, building a nuclear reactor?
Well, right now, these things are typically measured in dollars per watt. You talk about how many dollars per watt does it take to bring on a nuclear power plant. And right now, depending on who you talk to, somewhere between $4 to $6 a watt to bring on a light water reactor. The real one to beat is natural gas. You can bring natural gas power online for about $1 a watt or less. So it's very cheap. Solar and wind are higher than that. You know, solar is about $9 a watt. We are shooting to make Lifter competitive with natural gas. And so that means we need to get down in a $1 to $2 a watt generation range. Now, one of the parts with gas is it's rather inexpensive to build the plant. The fuel is most of the expense. So even though it's $1 a watt, there's still more cost in there in the form of you're going to be purchasing natural gas. And that price is very uncertain. So when you look at a lifter for $1 to $2 a watt, you're looking at a full cost there, because that will include the tiny amount of cost for the fuel. In fact, the fuel cost is so close to zero that you can safely ignore it. It's really the manufacture and operation of the plant.
Do you think that's one of the arguments, or one of the, I guess, difficulties in getting thorium adopted more widely? Is it that, you know, is there a powerful uranium lobby?
Well, I don't know if I'd call it a uranium lobby. There is a business model that works for today's uranium reactors, and it's a fairly simple business model, and it's worked for many years. Essentially, what they did back in the day was they would sell reactors pretty close to cost in order to lock in the utility to buy uranium fuel from a vendor. And they did very well making, fabricating the solid uranium fuel. It's very expensive, and it involves enriching uranium and fabricating it and so forth. You see these fuel assemblies. So in Lifter, that whole cost model goes out the window, because now you have liquid fuel. You don't fabricate liquid fuel. You mix it up in a pot, and it's a very, very low cost operation. So I don't anticipate that existing nuclear vendors who have a business model based around fuel fabrication and supplying that fabricated fuel to utilities will embrace this technology. It's somewhat antithetical to their business model.
Going back to how the actual reactors work, people, I'm just looking in the chat room, and people keep coming back to, nothing nuclear is really clean or really safe. Are there, and is there anything that we've missed talking about in terms of how it works, the resources that are required to build one of these factory built reactors, and then what goes into running it, and the energy required to start it up, and then how it continues running and producing power? Is there anything that we've really missed?
Well, let me take on that idea that nothing nuclear is really safe, and talk a little bit about radiation. Radiation is one of the most misunderstood ideas out there. I was amazed how as a fairly educated person, master's degree in aerospace engineering from Georgia Tech, I thought I was a fairly technical person. And when I began to learn about radioactivity, I thought, oh my goodness, everything I thought was just about wrong. And so you really do find very little understanding of this out there. So people think radiation's unsafe, nuclear means radiation, therefore nuclear can never be safe. One of the first things I learned is we live on a radioactive planet. In fact, we live on a thorium-powered planet. Thorium produces about 80% of the energy inside the Earth that drives plate tectonics, that drives carbon recycling, that generates our magnetic field, that protects us from the solar wind. We have lived on a thorium-powered planet for 4.6 billion years, and we will continue to live on a thorium-powered planet. What we're talking about now is using this natural gift more directly to make electricity here on the surface. So if you feel like thorium is somehow unnatural or against nature's plan, I would challenge that. I would say go learn how this planet runs and what the energy flows are inside the Earth. Without the energy from thorium, this planet would have died out billions of years ago as our magnetic field went dead and the solar wind stripped away our atmosphere, as carbon was not recycled when plates subducted over one another due to plate tectonics. So that's the first part, is to realize we are already living around radioactivity. And guess what? Life adapts to radioactivity. We undergo radiation damage all the time, mostly from going out in the sun. And our bodies have the ability to repair radiation damage. Now, what's important is that you operate in a way that you don't have too much damage at one time, just like anything else you do, like exercise or any other assault to the body. So the body's repair mechanisms can take care of that. And with regards to that, the radiation and the protection that we've learned how to use with regards to nuclear technology is wholly adequate to keep the public safe against harmful effects from radiation. We don't have this world where some people like to imagine if we didn't do nuclear, there would be no radiation. That's just not the way things are. And so to say that nuclear is not green makes me wonder, do you know, I would challenge your definition of green. You know, I would say nuclear is the greenest thing there is because that's why we have green in the first place.
Right. If we didn't, nuclear is what is a technology that actually produces the most amount of energy of any of the alternatives to oil or coal, the carbon-based fuels that we use. And in terms of greenness, cleanness, the cleanness of it is just how do we get rid of the waste? And what do we do with the waste?
Well, let me take that on if I could. Can I talk about that a little bit? Another really neat thing about radioactivity is radioactivity gets rid of its own waste. I spent a lot of time modeling each and every single fission product that came from fission. And I've put some of these codes that I've written on my website. You can go to and you can run them, where you can see how nuclear, the byproducts of nuclear fission evolve over time. When things are really radioactive, it means they're decaying quickly. They go away quickly. They turn into stable nuclei. If something is really radioactive, it's going away fast. And what I found was most of the products from nuclear fission are decaying to stability in a few days. A few take a week, a very few take a month, and then only a handful last longer than that. So when it comes to the waste, the radioactive byproducts from nuclear fission are decaying very quickly, and I would love to have extended conversations with people about each and every single one of these. I had a YouTube video from a talk I gave at Google last November where I said, is nuclear waste really waste? And I showed the results of these simulations, and it was an eye-opener to me that this is not nearly the problem that it has been made out to be by the in the public mind in general. And even in the nuclear community, I was surprised to find how little work had been done in this area within the nuclear community. So we have a pretty good story to tell, and I'm trying harder and harder to tell it.
And how is it coming across? I mean, you've had probably great reception from, say, the Wired magazine reader community, people at Google. You've been invited to speak at Google, but how do you feel like you're, considering how long you've been thinking about this technology and learning about it, and how much you've been working to promote it and to educate the public about it? How do you feel your message is getting out?
I really feel like it's going very well, and I'm very thankful for the response that we've had online. And really, it's not my message. You know, I was born in 1974. I was born the year they canceled this research in Tennessee, and I feel like all I've done with the blog is I've stood up and said, "Here's this amazing work that was done, before I was even born, and it looks so good to me. World, what am I missing here? Tell me what I'm missing." And what I've found, to my great gratification, is other people who are a whole lot smarter than me have looked at it and said, "You're right, Kirk, this looks pretty darn good. Why aren't we doing this? And how can we change that? How can we go get involved?" So I've been very happy that the message is getting out. Now, at the same time, I would love to be reaching, millions of people with this message instead of thousands of people. But these things, they take time. I'm glad we live in an age where we have the internet and we have things like this ability to chat on Skype and to broadcast these. I mean, think how this message couldn't have been gotten out even 30 years ago at this kind of speed. We can talk to people all over the world, and we can talk about this possibility. And I also feel like if people understand that thorium really is a compelling alternative to fossil fuels, we will make different decisions in the future, strategically, politically, internationally. We may be a whole lot less inclined to engage in certain kinds of conflict if we don't think that our national security depends on obtaining access to some kind of fossil fuel rather than to developing our own energy sources. That's my hope, because I really think that otherwise, the future is pretty bleak with regards to how things are going to turn out with fossil fuels.
Right. In terms of your interest in the subject and how you got into it, I mean, this is a technology that, as you said, it was being researched and was shut off before you were born. How did you get into it, and why the absolute interest in it?
Well, I've always been interested in energy. I think just about every engineer is interested in energy. Certainly just about every engineer I've ever met seems to want to talk about energy and energy supply no matter what their discipline. I was fortunate that when I started working at NASA in 2000, I had a colleague who had worked at Oak Ridge, and he had an old book on his shelf that was written in 1958 called Fluid-Fueled Reactors. And I just happened to pick up the book, and I said, well, what's this about? He said, oh, there was something they did at Oak Ridge a long time ago that, a different kind of nuclear reactor. He didn't know much about it either. And I started reading the book, and I really didn't understand it because I didn't understand nuclear technology. But I was intrigued enough that I began researching as much as I could. I was reading online. I was reading blogs, especially Rod Adams had I would call it a pre-blog. This was before people really had blogs, called Atomic Insights, where he had a lot of information. I started getting books from the library and began a period of self-education. And this went on for a couple of years. And I still felt like, well, I've learned a lot from books, but there's nothing to beat a formal education. And there's certain things you learn in a formal education that you don't learn from popular reading. And so I started a nuclear engineering program at the University of Tennessee. And sure enough, I learned a lot of things that I had not learned in the books up to that point. But to my surprise, each of them pointed that this was even better than I thought, that this was a really incredible technology. And my desire to advocate for it and to spread the word just kept growing and growing and growing. And
you have a family. You've got children. You're advocating for this technology. We've talked about the safety and radiation and all that kind of stuff. If you could build a thorium nuclear reactor, either in your backyard or in your basement, would you do it? Do you trust it that much?
Oh, I would. To say I trust my life with it is an understatement. I mean, think about the people in the Navy who serve on nuclear-powered vessels. They literally live right next to a nuclear reactor. And they're very happy to do so because that is a significant safety improvement for their lives rather than living on a fossil fuel-powered ship next to a huge tank of fuel that could be hit in a conflict and explode. And so I would be very comfortable living next to a lifter, and there would be a number of advantages from doing so. So yes, please put it in my backyard, or I should say I would like to build one in my backyard, and I'd like the opportunity to talk my neighbors into it too. I'll give them free electricity. So
right. Where would the thorium come from? So you said that it's really, it's abundant everywhere. If you had your own thorium reactor, where would you get it? Is it being mined currently, that it would be an easy to access material?
Kiki, you're going to love this story. This is just one of these you just couldn't make up.
Great.
About 2 years ago, we had our first Thorium Energy Alliance conference in Washington, D.C. One of the speakers was a fellow named Jim Kennedy, and Jim has been an incredible force in helping to wake our country up to the problem we're having with rare earth metals and our need for rare earth minerals. He talked about how the Chinese made a decision decades ago to sort of corner the market on this, and they did it very effectively. So he starts talking about a mine he wants to put in Missouri to mine rare earth minerals, and they're used in everything, mostly in green energy type products as well. Well, one of the interesting things about rare earth minerals is they're always found with thorium. And so he had come to this conference because he was trying to figure out what to do with the thorium. This is really bizarre, but when you mine thorium out of the ground, so this is thorium that's been sitting in the ground, when you take it out, right now the regulations say that you have to treat that like nuclear waste and you have to go bury it, which is really strange to me because it was in the ground right before you did this, and all you did was dig it out. So he came to this conference, and I said, how much thorium would you produce from your mine? He said, well, we think we're going to get about 5,000 tons a year. Now, this is without even trying to get the thorium. This is just in the course of trying to get the rare earth minerals. And then he said, Kirk, how much power could we generate from 5,000 tons of thorium a year? Unfortunately, I'd actually already done that calculation. I said, that's enough power to run the entire world right there. From one mine in one state in one place that's not even trying to mine the thorium. So then I said, well, how much would the thorium cost? And he looked at me and laughed, and he said, are you serious? I said, yeah. He goes, I'll give it to you.
Wow.
The alternative between having to pay to throw it away versus giving it. So getting thorium is not going to be hard. We are going to be mining for rare earth minerals, mostly to get neodymium for windmills, and we will be producing plenty of thorium without even trying.
That's just mind-boggling that it's a waste product, that it's something that somebody would be paying to get rid of and would be like, take
paying
it.
A lot of money to get rid of.
yeah, take it. I don't want this. You go power the world. Oh wait.
You go power the world.
That's an amazing calculation. Is it? I mean, how much thorium do you need for? You said a 1,000 megawatt reactor for, say, like a year.
About 1 ton. You and I could go to his mine and we could work for about 3 hours in the morning digging up ore, and we would produce enough thorium to run that reactor for a year. So with shovels, we wouldn't even need heavy equipment. So it's not hard to get enough thorium to run a reactor for a year.
Wow. Is there any processing of that thorium that needs to be done, or is it just right out of the ground? You can put it
has to be processed.
Yeah.
The rare earth minerals, the particular mineral that it's found in is called monazite, and it's a mineral where you can either have thorium or a number of these rare earth minerals occupying the same location in the mineral. And so there is a processing that's undertaken during the extraction of rare earth minerals, but this would essentially just be one more step on a 12-step process already. So it's something they're already going to be doing in order to get the rare earths.
Okay, so they're already going to basically be doing that processing. They're going to have it out, and then hopefully there will be thorium reactors. Thinking about China, there are other countries that are working on this as well. Are there any thorium, these liquid thorium reactors on the docket to be built in any other countries that, we're looking at, France, India, China? We're going to build one.
There is a small research program going on in France, and I met some of the researchers who are involved in this, looking at lifters and the use of thorium. But it's rather modest right now. It's mainly connected with trying to burn up some of the plutonium that they're producing in their nuclear reactors there. There's another program that's quite active in the Czech Republic, again at a research level, and I don't mean to disparage this because it's still bigger than anything we've got going in the United States, looking at lifters, and it's going quite well, but it's still quite small. The Indians have a large thorium program, but it's not based around liquid fuels. It's based around solid fuels. And when you use thorium in solid fuels, you don't get those kind of efficiencies that we're talking about with lifter. You're doing a little better than uranium, but not a lot better. And so I've tried hard to talk to any Indians who will listen about, why don't you look at lifter technology for thorium rather than solid fuel technology for thorium? But right now they're not taking that approach. So what's exciting about the Chinese development is they are taking the lifter approach. They're looking at the fluoride fuel form and thorium, and they're on the right track. And so it's time for other groups in the world to get on it as well.
Yeah, and since China is probably doing a lot of the rare earth mining, they've got a lot of thorium.
They have got a lot of thorium. They've already, I've been told sort of secondhand that their rare earth processing has been setting the thorium aside for years rather than trying to throw it away. And so they have vast amounts of thorium that they've already separated.
Wow, they've got backlogs. They're just waiting for the day that everyone else will catch up with them, and they'll be like, "You want some thorium? We got some thorium.
No problem. We got some thorium.
Just show me the money."
Well, they'll be disappointed in that because, as soon as mine number 2 produces thorium, the price of thorium will very quickly go to zero. So people ask me all the time, should I invest in thorium mines? And I say, no, that's not the thing to go after. The thing to go after is the machine that makes thorium valuable rather than the thorium itself.
Right. Yeah. So what do you think is the next step? What needs to happen? We've talked about education. We've talked about, getting people to understand the technology, to start talking about it more. But is the science and the engineering the next big step in developing this technology, or is it the political and economic side?
Yes. I think all of those need to happen. I think that the next step for this is for private industry to either embrace this or form to start doing it, or in some form or fashion begin working on this. I don't laugh too hard when I say this, but I think about, nobody had any idea on April 1st, 1976, that a company that would someday be the second largest company in the world was formed in a garage that day. Nobody thought 12 years ago when Google was formed that it was going to be a huge company.
Yeah.
New ideas are born all the time. New companies are born all the time. Most die, most fail. But I hope that we'll see a springing forth of entrepreneurs and people who are going after pursuing this technology and trying to bring it to market.
Yeah. Is there anyone that's particularly in the way that's blocking attempts to move forward? Or is it just, like you said, a lack of knowledge?
Well, I can't think of any active roadblocks right now to it. There's plenty of usual suspect roadblocks that will probably stand in the way. People not understanding the technology, especially at a regulatory level, inertia. One of my favorites is people saying, well, if it was so great, it would have been done before. And I want to say, well, that argument could be used to prevent any technological progress on anything in the future. And I get a moderate amount of criticism online about this. People, I saw an article the other day where I was called the lifter fanaticist in chief, and I thought, okay, well, I'll take that that mark if you want to call it that. I guess things that haven't been done before always seem a little crazy at the beginning, but I encourage people to look at the technology, to examine it on their own from an engineering perspective, if you're an engineer or a scientist, and to say, don't take my word for it. See if you think that this has the promise that I've talked about, because I think you will come to the same conclusion, that this is a remarkably promising technology that was probably overlooked for reasons that would not stand up to scrutiny today.
Do you have any suggestions that for people to go to educate themselves, to be able to think about it more clearly?
Thorium.com and come to our website, come to our forum, email me, Kirk F. Sorensen at gmail.com, and let's talk about it. We're having a conference, the third Thorium Energy Alliance conference in May. Go to thoriumenergyalliance.com and learn more about that. Please come to the conference. There's a lot of things you can do online now that before required you to be face-to-face with somebody. And it's one of the great things about the internet is that now we can have interactions and collaborations and move things forward even when it's 11 o'clock at night and you're in your pajamas. So, yeah, there's the website. Great. Thank you.
I'm in my slippers right now. So, yeah.
All right. See, there we go. And we're having a very pleasant conversation.
Exactly. For yourself, for full disclosure, there was somebody asking in the chat room, do you have any financial ties to Thorium in any way, to that other, or is this just purely intellectual and academic interest?
And until about a year ago, the answer would have been no. I had no financial ties to anything. I'm chief nuclear technologist at Teledyne Brown Engineering, and we produce nuclear equipment. And yeah, absolutely, we want to see this go forward. We want it to be profitable, and we want to be successful. I'm not sure to what degree. I need to make it clear. I'm not speaking for my company in that sense. They are interested, but they have not committed to building a lift or anything like that. But yes, there is. I definitely have a financial interest in the success of this.
It's a good job.
It's a good job. It's a great job. I love my job.
Yeah. What would you, going back to the idea of kids and the next generation? We're looking at where we're going to be leaving the world, and as we pass the world on to the next generation, what do you want to pass on to them?
Thank you for asking that, Kiki, because I have 4 children, and my 2 oldest have really embraced this. They're 8 and they're 6 years old, and they first learned about it when I started teaching them about what I called the electricity rock before they were old enough to understand what an element was or what thorium was. And now they talk about it all the time, and they wear their thorium T-shirts to school that say "Ask me about thorium" that we got from the Thorium Energy Alliance, and they recite the periodic table on the internet, and they ask me all the time, Daddy, how's it going with thorium? How's it going with the electricity rock? Because we want the air to be clean. They've heard me explain to them about what we're doing today, about how it makes the air dirty and it makes the water dirty, and it's not good. And my 8-year-old, I was taking her to school a few days ago, and I was describing to her things like this that we're involved in, and she turned to me and she said, "Daddy, I'm so excited." And that meant a lot to me, because I don't want this to sound trite at all, but my children are the real reason why I am pursuing this so intensely, because I'm very afraid of the world that they will be inheriting otherwise. We know that the fossil fuels are running out. We know that trying to get them will lead to conflict and war and economic downturns. How can we stop this from happening? We have to have a new energy source that is of incredible scale, that's big enough to replace fossil fuels, and that has the longevity to last for thousands and thousands of years, and that has the safety, and it has the abundance, and it's not in any one country, it's everywhere, and it's dirt cheap. I mean, it sounds like a fantasy that these things could really be all in one package. And that's why when I learned about the thorium story, I thought, this is a gift. This is truly a gift. This can be the end of our first era of human energy production. We can turn our back on fossil fuels as a society and move into a thorium age. I truly believe that 1,000 years from now, historians will mark a thorium age, and I hope it begins soon. It may not begin until long after I'm dead, but I will try my very best to bring it about, because I think it must happen. We must move into this new energy era. Otherwise, we are in great peril.
Well, thank you very much, Kirk. It's been really, really great talking to you. I really appreciate your time.
Thank you very much. I appreciate you having me here.
You're welcome. And everyone out there who's interested in finding out more about the lifter or thorium reactors, be sure to visit energyfromthorium.com for more information. I'm Dr. Kiki, and this has been Dr. Kiki's Science Hour. Next week, we're going to take a break from broadcasting. That's right, I'm taking a break. I'm due to have a baby, like next week. So we're taking a break. But beginning in March, the show will go on. The Science Hour is going to resume, and it's going to be hosted by some very special individuals, many of which you may be familiar with. And they are going to be choosing their own guests to interview. So it'll be a great surprise, I think. March is going to be a fun month in the Science Hour. So keep your RSS readers peeled for an awesome month. And depending on how things go on the pregnancy front, I'll be back in the driver's seat sometime mid-April is what I'm thinking right now, something like that. Until then, you can follow my science-y pursuits on the interwebs. As always, you can go to Twitter. I'm at Dr. Kiki, DRKIKI. You can find me on my Facebook fan page. Look for Dr. Kiki in Facebook. You can also subscribe to this show so you can listen to this episode again in case there were any details that you missed. You wanted to go back and listen to something? You can do that. You subscribe. You can do that by going to twit.tv/Kiki. That's twit.tv/KIKI. And I won't see you next week, but I will be back in the near future. I do promise that. And there will be more Science Hour coming up in March. Thanks for tuning in to the Science Hour. I appreciate all your support over the last 9 months as we've been developing our little science project here. And there will be more news on that when we return. In the meantime, remember, all it takes is 1 hour a week. That's all I ask to make your world a whole lot more interesting.